Hi all, welcome to another technical session on AMS applications. So in this session I am going to brief you about the spectral calculations, so how we can use AMS in spectroscopy calculations. So as an introduction I would like to say that the calculations refers to a family of computational tools in AMS which is designed to predict and analyze the spectra arising from electronic, vibrational and optical processes at the molecular and material level. So the capabilities are primarily handled through ADF for molecular systems, BAN for periodic systems, and the AMS driver, which manages the workflows such as geometry optimization, frequencies, and property calculations. So speaking about spectral properties, which are derived from a high-quality DFT or time-dependent DFT calculation using slider-type basis functions, relativistic options, and accurate numerical integration schemes. So you can see that this output of spectral calculations using ADF. So let me show you that how the input goes on, because we have taken the example of an ethane molecule. So before that, let me brief you that for molecular spectroscopy, Amsterdam Modelling Suite offers vibration spectra, which would be IR Raman, UV visible absorption, TDDFT, and several other applications, including NMR, among others. Vibrational spectra comes from the analytical or numerical Hessians, which provides normal modes, harmonic frequencies, IR intensities, and Raman activities. Electronic spectra are computed using TDDFT, giving excitation energies, oscillator strength, and transition assignments. So for core level methods, ADF provides a transition potential approach to obtain reliable core ionization energies and near edge structure. And speaking about materials, so this session will be brief for molecular systems as well as for material periodic systems. For materials, band extends spectral analysis to solids, surfaces, and one-dimensional and two-dimensional materials. It can compute phonon spectra, electronic band structures, density of state, optical properties, including dielectric function, absorption coefficient, and X-ray related spectra for periodic systems. All spectra can be plotted, broadened, and analyzed directly in the AMS GUI, which we are focusing in this interface, which provides interactive tool for viewing transitions, vibrational animations, partial density of state contributions, and symmetry analysis. If the user wants to provide a short workflow for performing any specific spectral calculation, we can demonstrate it using the applications covering up IR, UV visible, density of state, band structure, etc. So in the beginning, I have briefed some technical videos covering up the band structure using band engine. So let me show you that how we can use this specific methodology, that how we can do the spectral calculation for a simple ethane molecule and how we can do the analysis. So let me open up a new input. So I have already already uploaded a video that how we can upload a molecular system into this AMS interface. So let me show you. Okay. So I'm just searching that ethane molecule from the database. So just selecting the ethane molecule, and then I am setting up the symmetry. Okay, so the 3D symmetry is imposed, and I'm just changing it to geometry optimization, just checking at the frequencies, and remaining the correlation function, basis set, etc. I'm using it as default, and then I'm saving it. So let me save as SP02 because it's already spectral calculation. I have already saved it that file, and now once it is saved, let me go to file menu and press on run. So we can check the progress of that calculation. So the calculation is running, and if we go to the log file, we can see that how the the calculation is progressing. So this is actually the log file. So it's a fast calculation. So once it is finished, it will ends up with the normal termination message. So it will take only few seconds. So once the calculation is finished, we will check the output. So you can see this is the progress of that step. Result output file is generating, and now we can view the spectrum. So this could be the expected vibrational spectra of this specific ethane molecule. And if I press on the symmetry, so you can see the vibrational. So at that which point is that vibrational modes, and see on the right hand side this moving to the frequency according to the frequency, the intensity, and so this is actually the expected outcome of this spectral calculation. So you can see at mod A1G, the Gerard, you can see the frequency of 1400 centimeter inverse 1 and the frequency. So this is actually the expected outcome of this vibrational spectral calculation using ADF. In the next session, we will be focusing on for periodic system. Okay, so thank you.